So first we're going to look at directions inside of crystals. And so these conventions are used across all material systems and all crystal systems as well. So this is very useful across all of material science. And so for a specific direction inside of a crystal, we use square brackets. And so these square brackets tell us, all right, we're going to go in this one particular direction, and that particular direction is basically defined by where we choose to place the origin. So I'm going to start off here by placing the origin in the bottom right. And so this is going to be my x direction, my y, and the z going up here. And so let's first start off with an example of the 1, 0, 0 direction. So I'm going to go one full stop in the x direction, and so I can just draw that vector here. So this is the 1, 0, 0 direction. Let's do another example of the 0, 1, 0 direction. So I'm going to go one full stop in the y direction. Here we go. So 0, 1, 0, no problem. Now, the cool thing about, I guess it's cool because I'm a nerd, but the cool thing about these directions is that they just act as normal vectors, so you can add them together. And we'll use this property of directions and vectors to help us understand more complicated directions. So if we add these two together, we just get 1, 1, 0. And then you can just, use the in to tail approach to add the vectors together so that you can find this final direction here, which is going to be our 1, 1, 0 direction. All right, no problem there. So now, in general, if we want to talk about a kind of class of directions, we use what's called the family of directions. So these are denoted by angle brackets here. And as an example, the family of directions of 1, 0, 0. First of all, think about how many directions there are here. So I'm gonna, just take a moment here in a second to pause the video and think about how many unique directions are in the 1, 0, 0 family. So pause it for 30 seconds, work through it, and then come back. All right, so hopefully you were able to figure out the 6 directions. So they are 1, 0, 0, 0, 1, 0, 0, 0, 1. And also, there's the negative versions of these. So -1, 0, 0, 0, -1, 0, 0, 0, -1. Now, note that we don't put the minus in front of the number. This is kind of convention in crystallography and material science. Also, sometimes people will say instead of -1, and you'll hear me say this too, sometimes you'll hear people say bar 1, and that bar just represents the bar on top of the 1. So I always say bar 1, meaning it's like -1. Other people say 1 bar to mean -1. I think that's kind of confusing, but at least for this class, -1 is bar 1 and vice versa. All right, so these are the 6 different directions that are in the 1, 0, 0 family. Now, again, this is really only specific for cubic materials. You can't necessarily, just go through and find all the different directions just by permutating where 1 is at and then permutating where the -1 is at, because crystal symmetry denotes what family of directions are symmetrically equivalent. So now let's kind of try to use what we've learned so far to draw a slightly more complicated direction. And so that direction will be -1, 1, 2. So we're going to try to draw that one. So for this example, I'm going to place the origin here. And that's going to be my x direction, y direction, and z direction. Now, you can choose to place the origin anywhere you like, but the one caveat to this is that you really need to make sure to follow the right-hand rules. If you don't do that, then your answers are not going to be correct. So what do I mean by that? If you stick your index middle and thumb out, your index finger goes along X, your Y goes along your middle finger, and your Z goes along your thumb. So the right-hand rule, obviously. So for this direction, so I want you to try to draw this. So again, I'm going to pause for 30 seconds. I want you to try to figure this out on your own, and then we'll go from there. All right, so to draw this, so the first step, kind of gave you the first hint in the slide. So you want to scale the indices so that the largest index is not larger than 1. All right, sorry about that. We got a technical problem, so I had to restart here. So we're going to take the minus 112. We're going to divide it by 2 so that we can scale down the z index to 1. And so our new direction, which is still parallel, but the length is different, is going to be minus 1/2, 1/2, 1. And so what we can do is break this down into 3 different directions. We can use the additive property that I showed a little bit ago. And so this is going to be just minus 1/2, 0, 0, plus 0, 0, 1/2, 0, plus 0, 0, 1. And so we're just going to add all those up together, and then that will give us the final vector. So in the first case, we're going to go to minus 1/2, so we're just going to come down here. And in the second case, we're going to go over in the y direction by 1/2 over to here. So that's the positive y direction. And then to finish it up, we're going to go 0, 0, 1. So we're going to go straight up to the middle of the top. And that's going to be our final vector here. So I'm going to make this red. So we're going to go from the origin and up here. And so this is going to be our minus 1, 1, 2 direction. All right, no problem for directions. So now here's, now we're going to talk about planes in crystals. So for planes, for a specific plane, we use parentheses, as shown at the top there. And so the important thing to note about planes is that, well, let's say we're going to work with 1, 1, 0 for a plane. Now, the normal, a plane is defined by its normal, basically. So the normal in this case is parallel to the direction of 1, 1, 0. And so this relationship between the normal of a crystallographic plane to just taking the index from the parentheses, this is only strictly true in cubic systems. In others, it may or may not be true, so just keep in mind about that. But since we're only today working with cubic systems, the normal to the plane is also just the index of the plane itself. So as an example, we can draw this out. So if I take the origin to be here, and I'm going to make x come down this direction, y here, and z going up. So I know that our normal direction is 1, 1, 0. So I'm just going to go plus x and plus y, and I'm going to come across this, the bottom plane there. So that's just going to be the direction 1, 1, 0. And since I also know that this is the normal to the plane, then you can just kind of schematically, visualize where that plane might be. And we'll go over more specifics about how to construct these more complex planes here in a second. So now this plane in green is our 1, 1, 0 plane. All right, so now for a family of planes, we use brackets. So you can say squiggly brackets, or just I call them brackets. So for a family of, say, let's go with 1, 1, 1 planes, I want you to take 30 seconds and write down all of the distinct planes using parentheses. So take So pause the video, take 30 seconds to do that. All right, so starting with the 1, 1, 1, so we're just going to write down the same plane for this. Now, what we can do is to kind of permutate where the negative sign is at. So we can just put the negative sign on the first one, we can put it on the second one, and then we can put it on the last one. And now maybe during that 30-second break, you wrote out some other planes. So the other possibilities are just making basically the negative of all these planes. And so that's basically just multiplying the indices by -1. But in reality, this is not, these planes that I'm writing out now in blue are not actually distinct and different from the previous ones, because they still actually define the same planes as before. So it's just that their normal is in a different direction. So in reality, there's only 4 1, 1, 1 planes, and they are given in red or in blue. You can choose, which convention to use there. So for the family of 1, 1, 1 planes, there are only 4. And so if you have questions about that, feel free to ask me on Friday when I'm back. Excuse me. All right. So now we're going to go into a little bit more detail on actually drawing the planes. So the step to draw a more complex plane is to first take the reciprocal of all of the HKL, the Miller indices, and then to mark the axis intercepts and connect the points, connect the dots. So let's start off with a slightly complicated one. So we're going to try to draw the plane 1, 2, 3. And so to start off with, what we're going to have to do is draw the origin. And we're going to choose the origin and draw in your coordinate system. So X, Y, and Z. So the first step is to take the inverse of all of the indices. So step 1. So 1 over 1, 1 over 2, and 1 over 3. So what this means is that the plane crosses the x-axis at 1, the plane crosses the y-axis at 1/2, and the plane crosses the z-axis at 1/3. So this method is, you can use this pretty easily, and I'll show you some more complicated planes later on, and we'll go through solving those. So in the first case, I'm just going to draw the dot for where it crosses the x-axis at 1, draw the dot for where it crosses the y-axis at 1/2, and then finally at 1/3 for z. And then you just connect the dots, as I said before, and boom, there's your 1, 2, 3 plane. And so remember again that the normal in the cubic systems is given by also the Miller indices. So you can also say that this direction, even though you can't really visualize it like this, but its normal direction is parallel to the 1, 2, 3 direction. So let's do an example of doing the inverse. So here I'm showing a plane that's already drawn in red on the right-hand side. And so let's try to figure out what that specific plane is. Well, again, you can probably inspect it and see that it's a 1, 1, 0 type plane. But what we have to do, though, is draw in the origin. So I'm choosing the same origin as before, so X, Y, and Z. And so we're just going to work through the same steps as before, but just go in reverse. So the first thing that we're going to do is record where the plane intercepts all the axes. So for X, Y, and Z. So for X, where does it intercept the x-axis? It doesn't, so it's 0. For Y, where does it intercept? It intercepts at 1. And for Z, it intercepts at 1 as well. So then we're going to invert the indices, and it's just going to be 1 over 1, and 1 over 1. So we're left with the plane, the specific plane 0, 1, 1. So that's how you go through the process of, seeing it and then figuring out the specific plane.